Good evening and welcome. Thank you all very much for coming tonight for our Autonomous Perspectives event. And I want to start off by saying thank you to Cal IT2 and especially to Ramesh Rao for allowing us to conduct these experimental conversations across the arts and sciences. And Cal IT2 has been a really important site for us for interdisciplinary conversation in the visual arts. And we hope that you will all take some time to see the exhibition that has occasioned this conversation tonight, the exhibition Autonomous, which is at the gallery in the lobby. So the talks tonight relate to the themes of Autonomous. And I want to give you just a short introduction so you have a sense of what those themes are. Autonomous weapons, self-organizing systems, the Internet of Things, self-driving cars, intelligent environments, smart structures. In one way or another, we're all hearing about the rise of intelligent robotics and automated technologies. Through materials technologies developed to harness new sources of energy, and through embedded networks of computation, aspects of our world that were formerly considered inert are now endowed with communicative ability and intelligence. As capacities of sensing, processing, transmitting, and actuation are woven across the boundaries of the object world at multiple scales, novel forms of agency arise. Forms of agency that can communicate and respond to change in ways that often bypass the sensory and cognitive capacities of humans. To what extent can we regard these forms as autonomous? This is one of the central questions of the project. In the visual arts, there's a long history for thinking about the autonomy of objects and the autonomy of perception. And while this is in many ways a different historical and critical sense of autonomy, there are some of the basic ontological questions still resonate. As vision increasingly becomes a component of new machines and apparatuses, for example, where is the body? And what about the subject-object divide? Today, philosophical pursuits across the visual arts, humanities, and sciences increasingly situate agency across the bounds of subjects and objects in new clusters. Gaining momentum in the aftermath of the semiotic paradigm, they bring an understanding of matter and objecthood rife with subcognizing ability, transmitting electrochemical and vibratory energy, sensing and storing change, however technologically enhanced it may be. So these are some of the main concerns explored in Autonomous, and specifically our presentations today will be concerned with autonomous weapons technology, automated software and design, adaptive materials and structures, and autonomous art objects. The presentations will range across current work in computer science and engineering, mechanical and aerospace engineering, science and technology studies, architecture and design theory, material culture studies, art history, and philosophy. We're going to try to do our best to avoid too much specialized language, but as you know, working across disciplines can be difficult and challenging in this way, so we hope you'll bear with us if at times things become a little too opaque. We'll have some period of conversation after the presentations and a reception following for further conversation. So we have the order of speakers tonight. We'll first hear from Ryan Bishop, who is Professor of Global Art and Politics at the Winchester School of Art, University of Southampton in the UK. His research areas include critical theory, cultural studies, visual culture, architecture and urbanism, aesthetics, critical military studies, and science and technology studies. His newest authored and co-edited books include modernist avant-garde aesthetics and contemporary military technology, technicities of perception, visual culture, and comedy and cultural critique in American film. His talk today is called Farther Afield, the Cultural Politics of Remote Sensing in the Long Cold War. We'll next hear from Benjamin Bratton, Associate Professor of Visual Arts at UCSD and Director of the Center for Design and Geopolitics. As of this summer, he is also faculty at the European Graduate School. His research is situated at the intersections of contemporary social and political theory, computational media and infrastructure, architecture and urban design. His current work focuses on the political geography of cloud computing, highly granular universe addressing systems, and alternate models of ecological governance. His talk today is called Autonomy as Abstraction, Notes on Robotics and Material Composition. We'll next hear from Robert Skelton, Professor Emeritus in the Mechanical and Aerospace Engineering Department at UCSD, where he was the Daniel L. Alspach Professor of Dynamic Systems and Controls. He joined UCSD in 1996. From 1975 to 1996, he was at the School of Aero-Astro Engineering at Purdue. And from 63 to 75, he was at Lockheed Missiles and Space Company and then Sperry Rand, where he worked on spacecraft control, Skylab, and Hubble Space Telescope. His work integrates the design of structures and their control systems, advancing a paradigm for adaptive structures called Tensegrity. In his talk today will be on deployable Tensegrity structures. And then we will hear finally from Peter Ballantine, who is a leading expert on sculptor Donald Judd, having worked extensively with Judd from 1969 into the artist's death in 1994. He was directly responsible for the fabrication of over 200 Judd works and has been closely involved in the authentication, restoration, and display of Judd's work, curating a number of Judd's exhibitions on Judd's work over the past several years in London, Cologne, Madrid, and New York. He has served as art supervisor of both the Donald Judd Estate and the Judd Foundation, and is currently working on a book-length study of Judd's work called The Philosophy of Real Objects. And today he will talk about transferences between the process of fabrication and the specificity of material form in the work of Judd. So please welcome our panelists, and we'll first hear from Ryan Bishop.
Thank you very much, Jordan. Thank you for inviting me, and thank you, Trish, for all of your help. It's a great honor for me to be here and to share the dais with my old friend Ben Bratton and with Peter and Bob. So thanks. I'm mostly going to read, so apologies. Even though I teach in an art school, I come from a text-based background. So what I'm really going to be talking about in this particular talk is a range of geopolitical situations that have led to the emergence of a series of remote sensing systems, how they operate, but more importantly, what they do for our thinking about subjects and agency, and particularly the political subject as an agent. So I'll wrap that around kind of near the end and to lead us to think a little bit about the auto in autonomous and the nomos in autonomous to tie it up with the exhibition. So one legacy of what's been called the Long Cold War can be found in the multiple large-scale interrelated remote sensing systems that are operative today. Smart dust, for example, and we've got a little image here, and I'll have a few more, and I'll talk about it a little bit later as well in more detail, constitutes the basis of polyscalar computer systems of remote sensing at micro levels and relates to ubiquitous computing, pervasive networks, and utility fogs as potentially transmitting endless streams of real-time or stored data. Developed initially for DARPA, the technological R&D arm of the U.S. Defense Department, Smart Dust started with the work by Chris Pister and his team at UC Berkeley, who referred to the project as autonomous sensing and communication in a cubic millimeter. In a glimpse at the not-too-distant future, Hewlett-Packard intends to distribute 1 trillion of these microsensors from the bottom of the ocean and up into space in a project they are calling the Central Nervous System of the Earth. The history of remote sensing is the history of media generally, especially electric and electronic media. Remote sensing is implied in all teletechnologies and thus finds its earliest imaginary possibilities in the age of telephony, telegraphy, and radio, along with the attendant avatars of subjectivity capable of experiencing sensorial phenomena at a distance. Science and technology reconfigure the imaginary such that they can decontextualize the observing subject from the time-space constraints of the corporeal body, thus repeating Martin Heidegger's famous dictum that the essence of technology is nothing technological. It resides instead in the immaterial, the noetic influences that render the world possible and render the world malleable. The physical constraints of nature become those areas that certain forms of technoscientific inquiry wish to erase or turn to their advantage, as made manifest in remote sensing systems deployed by various militaries, especially through optoelectronic devices, operating at a distance and overcoming space to operate in a real time of control. With the Limited Test Span Treaty signed in 1963, and 1963 comes up a few times in this as a sort of a almost 50 years ago marker. With the Limited Test Ban Treaty signed in 1963, nuclear testing literally went underground, forcing innovations in modes of remote sensing for purposes of verification. Though these innovations, especially for sensing other than the visual, helped fuel a range of interrelated research leading to an immediate precursor of smart dust, and this was Operation Igloo White in Vietnam, which was begun 3 years after the treaty was enacted. Scopic regimes became increasingly synesthetic. That is, they yielded to remote sensing generally, using all of the sensorium to map or see the terrain of battle, a process begun in the early part of the 20th century. Because so much of the teletechnological development, as McLuhan, Baudrillard, Virilio, and many others have explored, depends on the understanding of the subject as an agent enacting its will upon objects in the world, including other subjects, the means by which we can and do imagine extensions of that sensing and acting self, invariably fold into and influence the interpretation of that self. So we take these remote sensing systems and we project them out into the world, and they come back and feed back to us in an almost cybernetic system, a way of understanding what that self is and how that self can operate in the world, essentially. Multisensory teletechnologies, as they pertain to the implications for the enactment of agency, relate fundamentally to the constitution and expression of the political subject and the many systems in which it is embedded, formulated, constructed, subsumed, and articulated. Remote sensing and teletechnologies, as mobilized by the military, have the potential to result in killing at a distance, which is clearly a matter of a subject controlling and manipulating objects, even unto death. However, the far greater sense of the self as agent in this scenario emerges in the belief that one possesses the power to control that distance, to alter proximity and render a plasticity to its measurable materiality. The casting of the senses and the central nervous system beyond corporeal bounds, therefore, has profound ramifications for imagining the political subject as agent and further for the conditions of thinking the autonomous. So that's kind of the intro. Everybody doing okay? Yeah, having fun? Yeah, it's good stuff. Okay, good. Okay, great. Moving on to smart dust. I've got a quote from Eliot, but I'll leave it for now. And I'll move up here. There we go. So this is the sort of thing that they're developing, right? And that's the size of smart dust. Each generation generates its own dust. Ubiquity itself, dust marks time, movement, and stasis, while evoking mortality. It is aeolian, wafted on the air, and carried in the atmosphere. Composed of animal and human skin and hair, industrial pollutants, fibers, particles from outer space, plant pollen, technological and agricultural residue, dust constitutes a microscopic encyclopedia of the minutiae of quotidian existence. The dust we'll take up here, though, is a specific kind of dust, one primarily of the imaginary at the moment, but inching its way closer to actuality, generated from and for emergent urban conditions, most specifically those pertaining to warfare. It is called smart dust. As mentioned earlier, it deploys ubiquitous computing, pervasive networks, and utility fogs to transmit continuous streams of real-time data and can be used as well to broadcast stored data for mixed reality sites. Each chip contains sensing, computing, wireless communication capabilities, and autonomous power supplies within its volume of a mere few millimeters. This autonomous sensing and communication in a cubic millimeter contains a host of governmental, industrial, commercial, medical, and military applications, as well as multiple profound implications for understanding human positioning and intervention into the world. As yet another manifestation of the myriad ways in which nanotechnology is being mobilized, the concept is to distribute very large numbers of wireless microsensors/transmitters by scattering them across a fairly contained space. Smart dust depends on the convergence of three technologies: digital circuitry, laser-driven wireless communication systems, and microelectromagnetic systems. The sensors spark off one another, detect the terrain, and speak to other machines. Smart dust, as envisioned and advertised, would work with 7 different levels of coordinated networks stretching from the ocean floor to terrestrial domains, including products, to the air and on into space. Hewlett-Packard plans, according to its own PR, to provide sensory capacities to extant IT infrastructure so that it will no longer be inert material and media, but active sensing devices. So that this infrastructure can see, feel, hear, and smell, Hewlett-Packard will deploy 1 trillion sensors the size of a grain of sand in the next few years that will operate under the label of the central nervous system of the Earth, which is also cutely anagrammed into sense, central nervous system of the Earth, right? So it's sense and sensing. Very cute. Sense becomes, in essence, the signature for the future of complex remote sensing systems. However, the ambitions explicitly outstrip the parameters of our planet and provide an exemplar of the kind of polyscalar computing that we are building and which by reversal and extension is increasing building us through a malleable imaginary of protean selves, occupying a protean world in which, to paraphrase Virilio, the infosphere controls the geosphere. And Benjamin Bratton, in his work on the stack, has written about this very nicely. This stuff, smart dust, is clearly not your common household dust. Rather, it is high-end, high-tech designer dust for the information wireless city and other kinds of terrain. It has a range of potential applications, including information about products, about the status of buildings, all sorts of different things. But it was primarily designed for DARPA, and it caught DARPA's imagination, who seeded the initial research as yet another way to expand the extent and massive defense-related sensing networks for battlefield surveillance, treaty monitoring, weapons inspection, movement detection, etc. These then become sensorial supplements of already prosthetic teletechnologies, right? So you have the teletechnologies, and these are further prosthetic extensions of them. So they are more extensions of these technologies than they are of any sort of corporeal self. Smart dust, especially as envisioned by Sense, constitutes an exponential expansion of the weapons ecosphere, as well as an expansion of the belief in the control and the autonomy of that ecosystem that is now literally made ecosystem. These fully automated machinic communication systems, programmed to track and monitor the state of circumstances, provide one of the most significant ways in which the militarization of everyday life invisibly operates in urban environments. At the core of the operation of these tracking and sensing systems is the software that programs the conditions they are designed to sense, monitor, and respond to. The politics of programs and the algorithms of urban control encodes and manifests the desires of specific interests within the urban landscape. So what appears to be a machinic, objective system of observation and monitoring, just a view of the cityscape or terrain, is anything but. It is a view with an interest. A key point of departure for the designs operative in urban sensing, tracking, and targeting can be found in the military plans for fighting in the tropical jungles of Southeast Asia. The response to guerrilla fighters along the Ho Chi Minh Trail, known as Operation Igloo White. The operation included 3 separate triangulated areas: the trail itself, laden with sensors related to every sorts of sense that you can imagine, a computer interpretation center in Nakhon Phanom, Thailand, and the airspace above Vietnam and Cambodia. The first was populated by guerrilla fighters and peasants, the second by US military intelligence officers and systems operators, who did little except keep the automated system running and update data so that it could influence future programming and action, and the third by fighter planes. The closed system of Operation Igloo White followed an automated set of program cause and effect actions and reactions meant to remove humans from the loop of sensing and tracking and to reduce the gap between perception and action, that is, perceiving a movement and firing upon it. The sequence went as follows: sensor detection became radio coordinates sent to airborne fighter planes, F-4 centers lock on target, auto guide and autopilot of fighter planes, auto fire on top at target on map grid, explosion. All of this occurred in the time span of 5 minutes. Jaw-dropping rapidity then, but agonizingly slow today. The command and control center never saw electronic information and data sent from the trail, and the pilots never saw the target. The entire closed system had machines reading machine-generated data to speak to other machines and automatically cause them to act on this information. Of course, the Viet Cong ascertained the interrelated parts of the operation and its fully automated nature, and thus circumvented the entire operation. They even turned the system's supposed advantages against itself through a number of ploys. For example, sending an unsuspecting water buffalo down a part of the trail to be blown up by the most high-tech weaponry available to the mightiest military machine in the world, while Viet Cong materiel and personnel bypassed the targeted area, this causing U.S. forces to waste money, time, and ordnance killing a non-target. The countermoves to massive attempts to incorporate horizontal diffusion into vertical control provided the Viet Cong with tremendous strategic advantages, especially as the U.S. forces continued to believe in the success of these systems. Operation Igloo White prefigures all of the intelligent material systems that Smart Dust promises. To pay tribute to this complexly enmeshed automated remote sensing system called Operation Igloo White, and as a progenitor of the current systems, one of the nanochips for Smart Dust is Actel's Igloo Nano FPGA. And here I've got a little picture of it. And there's Sense right there. And there's some military applications. I like this one because somehow it's the French Foreign Legion, and I'm not quite sure how they get involved with it. But there it is. And I don't know if you can read it, but right there it says Igloo. Smart Dust has a more stationary urban counterpart, Smart Buildings, which Jordan Crandall has written about most evocatively. With buildings and infrastructure outfitted with sensors to detect stress, shifts in normal states, the role of the intelligent built environment changes in numerous ways, including ways that could be mobilized for surveillance and action as on the Ho Chi Minh Trail. Previously, intelligent spaces, or smart dusted areas and buildings, have only been internally intelligent, speaking to themselves while monitoring the internal systems that observe their interior and their perimeter. Now, in an effort to safeguard the operations of the systems essential to the building or infrastructure, intelligent material systems have become externally intelligent, conversing with and tracking the environment with external machines that monitor the larger environment in a sustained engagement with the urban, natural, and meteorological contexts, as well as being in conversation with other machines residing outside the integrity of the built structure. The prosthetic extensions that so constitute a range of teletechnologies for corporate, governmental, and military operations for humans have now been granted to buildings, highways, water pipes, etc., but with the same goals of maintaining specific proprietary interests of property and wealth. and influencing behavior through the managed control of time, space, and populations, along with the added threat of mobilized violence, police, or military to so manage. When the dust settles, when the smart dust settles, it will have been fueled by the desire to eliminate the event, to make sure no event occurs. It is worth noting that DARPA's website slogan is, quote, creating and preventing strategic surprise, end of quote. However, the elimination of the event will have been determined by an indeterminate object that senses as a subject, communicates as a subject, and yet does not and cannot enact its own will, merely a node in a network shuttling data. Smart dust will have become us, the political subject without agency. The Limited Test Ban Treaty provides an important moment in the development of many remote sensing systems operative in the past, present, and future, including projects such as Transparent Earth. I've got a picture related to that. There we go. This is the generation of artificial lightning for Project Transparent Earth. Project Transparent Earth is a project combining weather hacking and artificial lightning to create the conditions in which synesthetic televisual mapping of the first 5 kilometers under the Earth's crust can occur. It couples with, going underneath the surface of the Earth, the very remote sensing Mercury, Mentor, Magnum, and Advanced Orion eavesdropping satellites in geosynchronous orbit that look like umbrellas the size of American football fields parked in space. LTBT coincides with the emergence of the prefix geo, becoming synonymous with the Earth as globe, as bounded, strategically networked and surveilled entity, a moment marked by the first issue of the Journal of Geoelectronics in 1963, which included an introductory meditation on the changing understanding of the prefix geo. The journal is now called the Journal for Geoscience and Remote Sensing. As the LTBT became the Comprehensive Test Ban Treaty, there was also developed the Global International Monitoring System, all of it just a glorified version of Operation Igloo White. Now I'm going to talk briefly about the autonomous and move towards wrapping up, which is probably good news for all of you. The autonomous. When Blaise Pascal, in the mid-17th century, crafted 3 documents intended to explain and provide him exclusive control over his mechanical calculator, he relied heavily on its performativity to justify the apparatus's virtue over those of humans. The superiority of the machine was not simply speed and efficiency, but its capacity to stand in for, to extend, or even replace the mental operations of its inventor. In fact, the user might not even possess these capacities at all. Of the machine, Pascal explains that it can, by itself alone, without any work of the mind, perform the operations of all parts of arithmetic. Pascal's machine, this is 17th century, neatly delineates a set of functions and qualities central to automation, including storage, repetition, production, substitution, and performance. The inventors or programmers of any machine or set of machines reside both inside and outside the machine. For the performance of the machine depends on its inventors to an extent for what it performs, but its performativity does not depend on its inventors once rendered operable. The performance can, and usually does, continue after the death of the inventors and regardless of any particular user. That it is self-operational highlights the auto portion of automation and sets up the tension between techne and logos resident in the term technology. That is, what is true of the machine, techne, is also true of the text, logos, and this is an insight that runs throughout the work of Jacques Derrida, for example. The death of the inventor, like the death of the author, that nonetheless allows for the survival and performativity of the machine or the text, is by no means the death of the sovereign subject. as numerous other pretenders to the throne stand ready and waiting. But the dispersed, distributed, and automated subjectivity and agency operative in remote sensing, especially closed automated weapon systems, might well wound, perhaps mortally, the political subject as a concept. Our common sense narrative states that when constituting the subject, political or otherwise, we set a scene of the sensing subject, solidly placed amongst objects through which we enact our agency. And any technology that helps us to so understand that scene, that is, all sensing technology, but most especially visualizing technologies, is also out there and external to the subject. This technology is part of what helps subjects place objects in the scene to realize their status as subjects. This reinforces a comforting story, a common sense tale of agency, subjects, action, and technology that allows us to fulfill our desire as autonomous actors, despite the division between external and internal as increasingly difficult to maintain, insofar as the subject and technology are concerned. It must be noted, though, that the subject-technology divide is in fact a blurry boundary that reaches all the way back to antiquity. Integral to the complex remote sensing systems generated in the wake of increased telesurveillance instigated by the Limited Test Ban Treaty is the auto, that self-generating element of the machinery and its programmed engagement with the globe, its inhabitants, and phenomena, which is one of the very selling points that Pascal makes in the attempt to secure exclusive production rights of his calculator. The auto, the term auto, functions as a hinge between the event, which is organic and animate, and the machine, which is calculable and inanimate. The all-important space between the event and the machinic is filled by the auto. If we examine the usage of this prefix, auto, over time, we will notice that the prefix, over time and usage, performs its content. This affix is self-performing, almost autogrammatic or autosemantic. Auto in Greek was not frequently used, but when used, it was in combination with other terms and meant self, one's own, by oneself, independently. Its usage becomes more common and prevalent in medieval Latin and into English, where it becomes a living element, prefixable and attachable to scientific terms to mean an action or an operation. And so this move from self to action or operation is important to our understanding of what the auto means in autonomous. The self of the Greek becomes subsumed in the English action or operation of systems apparently driven by an internal machine, energy, or desire constitutive of an entity resembling a subject, but not necessarily a self. Remote sensing systems, as metonymically invoked by smart dust and sense, are not only automated, but also autonomous. That is, once they are set up, they can and do operate on their own. These systems are self-governing, as the terms auto and nomos would imply, with nomos being one who deals with a set of laws, and the related nomia indicating a field of laws or principles governing a subject. The provocative political thinker Carl Schmitt discusses the nomos as the measure from which all other measures emerge, thus constituting a story of origins concerning how the division and partitioning of the world occurs, coming as it does from the verb nemen, to divide and thus distribute and allocate. And so nomos also means law, right? The nomos is the measure that brings about other measures, the measure, as it were, and is simultaneously physical, conceptual, institutional, and political, for it becomes constitutive of law and of tradition. It is the mark, the grammar, the limit, the cut. The basis for a taxonomy, the division of the world into parts and wholes, including states. The nomos marks the difference that makes a difference and is constitutive of difference itself. It forms the basis upon which we interpret the one and the many as the one and the many, and parts and wholes as parts and wholes. The nomos is that intractable problem in Kant's essay on perpetual peace, in which all people have equal right to the face of the earth, but nonetheless are an affront to one's neighbor simply by claiming that right. That claim to a spot on the face of the earth comes about through the division wrought by the nomos. The act of making this division, or mark, is a cultural technique that in middle voice fashion crafts the subject performing the act into a different kind of subject, in both grammatical and ontological senses. In an essay on the German traditions of thought surrounding Kulturtechnik, Jeff Winthrop Young cites the example of the humble plow, through which the act of cutting the land establishes the farmer as a subject, as a citizen, and indeed as a farmer in the same instant. The cultivation of a culture results from that incision of the land. Caroline Visman continues this same point by saying, one must therefore draw a distinction between persons who de jure act autonomously and cultural techniques which de facto determine the entire course of action. To inquire about cultural techniques is not to ask about feasibility, success, chances, and risks of certain innovations and inventions in the domain of the subject. Instead, it is to ask about the self-management or autopraxis of media and things which determine the scope of the subject's field of action. Such thinking on cultural techniques is related to, but different from, Yeats's famous rhetorical question posed in his poem Among Schoolchildren. How do we know the dancer from the dance? And even Irving Goffman's performance of everyday life. But it differs from these by foregrounding, as with language studies, the productive and generative roles of media and techne. The supposed autonomy of the subject, or the citizen, continues to be produced through current techne and has been dispersed into the electronic and digital operations of these fully automated systems. Rather than being a threat to humans, though, perhaps they merely embody what has always been the case, the political subject as wholly constituted by those laws and techniques that make people into subjects, with the failure of autonomy being the necessary condition by which the subject comes into being. That is, we have always been like these remote sensing systems that seem so alien and fearfully anti-humanist. We have always been the political subject without agency. Thanks.
Thank you, Ryan, and thank you, Jordan, for the invitation to speak with you today. Fortunately, I have a lecture that I need to do, an undergraduate lecture, shortly, and so I'll have to leave you a bit early before the entire discussion is done. So let me set my timer with this as well. I also want to say that what I'm going to talk about today is a sort of beginning of a project, and that I've begun. I've just finished a book, as Ryan said, on the idea of the stack and the nomos of planetary computation. And the next project I've begun is on robotics. And so what I want to share with you today is some of the initial thoughts on this, and less in terms of sort of something that's fully baked, more just a kind of index of ingredients that will be that might go into this. We can think of it in a way as a kind of open sourcing of this process. The title of the talk, Autonomy as Abstraction, actually comes from Chris Anderson, the former editor of Wired, who now runs a consumer drones company whose factory is based just down the road in Tijuana, that I will be going and visiting next week, and we'll report back to you on what I find there. And the idea of the autonomy of abstraction comes from a Google talk that he did, where he's talking about the fact that for this consumer drone, the drones that you fly, for the Anderson's drones, you fly them through the iPad, right? The drone has a camera on it, and you move it through the iPad. You don't actually pilot the drone, in the sense you're not telling it how to fly. You merely point where you want it to go, and it goes there itself. So what he's figuring is that in the process of piloting this thing is abstracted to a level by which the user, if you are still the user or viewer or everything, merely indicates on some level the type of flying or the location of the flying or the destination of the flying, and that the lower level works is actually taking place in a way in which that's unavailable and uncontrolled to that subject in some sort of way. It's an open question, though, as to exactly where the abstraction, which is autonomous then? Is this the intention of the piloter or of the device itself? And I guess that's part of what starts this. In a way, I think that, at least initially, this project for me could be divided into three sort of overarching areas of inquiry, and then I'll go into some of the subject matter with this as well. First, it has to do, and in resonance with some of Jordan's initial remarks, on matter itself, and thinking about or locating the question of robotics within a longer history of how it is that at particular points in time and in different ways, we come to assemble matter in such a way that we believe it to have some capacity of intelligence, and we recognize an intelligence in it, which can mean, of course, lots of different things. On the one hand, this might be thinking of sort of robotics as a subfield of chemistry, but it also may be in a way sort of a subfield of theology, in the sense to which, under earlier times, the way in which that we would assemble matter and indicate that it had imbued with some sort of intelligence was through a kind of ceremonial logic by which things become totemized or they become sacraments or in these kinds of ways. And perhaps part of the ways in which that we have trouble dealing with and talking about technology is that the ways in which that we do assemble matter and talk about it and imbue it with intelligence is done so in a way that's sometimes outside of the kind of integral organic narrative logics of those kinds of ceremonial indications, that these objects they themselves don't have a subjectivity or a role to play within it as well, and so their alienness seems that much more troubling to us in one way or another, and perhaps that could be something to solve. Which would then lead, it seems to me, to some questions about the space of a kind of generic or universal reassemblage of matter that some of the more utopian nanotechnology discourses about atomic level design may point us to, in addition to questions of universal addressing, deep address, which I've talked a bit about, and how it is that these instances may have a kind of a coherence to each other. But at the same time, then, it would suggest that it's absolutely essential to locate at least the philosophical question of robotics and this assemblage of matter within other within these traditions of myths. For example, the golem, right, in the Judaic myth of how it is that matter is put together and becomes this creature that has this sort of heroic work. Prometheus and the rest of this. These are part of what we're doing. Second, on this question of intelligence and how do we recognize the intelligence within this as well, would be to begin with the presumption that the Turing test model of the recognition of intelligence is fatally flawed. And it's fatally flawed precisely by its anthropocentrism, by that the condition for the recognition of intelligence or of subjectivity or agency is defined by a mimetic empathy, that it is like me and therefore it is intelligence, that the kind of Cartesian, Kantian condition of intelligence becomes a criteria for this as well, which may even seem a step backwards from this as well. And to the extent to which we may, at some point in our lives, be living with a lot of different forms of synthetic intelligence, may even be taken as a kind of racism. Third, to locate this within a concept of what I call the post-Anthropocene, which is to really sort of think about these within a larger and deeper question of a geologic, geographic, and political order in which humans are not the predominant agent or subject here as well, which would again point to not only the problem of the Turing test, but also to, say, Asimov's laws of robotics, where the robot will not kill people, it won't do this, and through things as well. This kind of Kantian legalism, presuming that the intelligence of the robot would have some capacity to comport itself and to think about itself in this matter, that the precondition of its intelligence could come to this, and therefore assume these laws is, I think, deeply unhelpful with this. Okay. So, to some of the topics I think that would sort of to think about this location is first this issue of matter and materialism. One of the most interesting panels I've been on in some time was an event that in New York called Google Arctic Mars, which I won't go into. But one of the persons I was on the panel with was a woman named Lynn Rothschild, who is an astrobiologist. And she finds, used to be sort of looking for little green men, and now is looking for, things on asteroids and figuring this out as well. And one of the questions that was put to her was about the table of elements. We have a certain number of things as well, and the question was asked to her, have we found anything on anything that we've got come from outer space to suggest that the table of elements may go much further up or much further down in a particular direction, right? It used to be thought in the late 19th century that there was this whole field of transuranic elements. There could be hundreds of more elements above this as well, and that maybe they go in an arc and stabilize, and something, when this as well. No. Pretty much what we know, the table of elements, is pretty much everything that's out there. Matter is a closed set in that regard. Now, so the implications of this for the Golem myth, Prometheus, Frankenstein, Jesus, other zombies, and so forth and things, I think, is rather sort of profound, and we'll get to the starters. Okay, drones, which, as I said in a recent talk, phones, drones, and genomes, that's what we do here in San Diego. The development of drones as these optical machines, flying cameras, and the rest of this as well, suggest in a way that we're developing, among other things, to think about robotics in terms of a kind of zoology, that there's a zoology of creatures at work. And there's even this great poster you can download that's a sort of drone identification chart that if you live in an area that's perhaps harassed by drones, you can look at this and get the profile and see what's exactly what. We have Google driverless cars, which are a kind of genre of drones. There's a new optionally piloted planes, with the kind of genre of drones. Google's recent purchase of Boston Robotics and those big, huge dogs that carry things up, land drones, they could be sort of called, suggests this in a way. And I guess within the sort of the earlier pre-zoology of this as well, maybe we think of the UFO culture of the 50s and 60s as a kind of drones from another planet that may have come to harass us at another certain point in time. But it also, I think, raises questions about who and what is a user within these kinds of contexts, and in the development of things like industrial internet and intelligent supply chain systems, where the terms of that networkicity actually comes in. Okay, to Google then, and the Google bots, and what it might mean that Andy Rubin, who was the guy in charge of the Android operating system, is now in charge of Google's new robotics wing. What does Google want with robots? How do robots fit into the larger question of a planetary computational hardware-software stack? Where are they in this stack? What is their role? It's unclear at this point what they might do. But the idea of robots as part of the terrestrial footprint of the cloud, not as sort of machines that have a bounded internal intelligence, but simply like any other piece of cloud hardware that is part of the sort of larger question of the network, also raises strange issues about where, in fact, the user conditions would apply, and where the autonomy and the rights of autonomy of the ownership versus the use of this may, in fact, work out, and in terms of which those robotics become part of our body, in relationship to our body, that the governance and sovereignty over those types of uses becomes interesting in a way in which we sort of need to deal with. Cory Doctorow had this example he used at a talk at Google where he was talking about, if you have, let's say you have a artificial eye, something like this, going on this as well. And the terms of this and the capacities of it, its computational processes are a cloud-based mechanism. If you go behind on your payments, you can't go on. Your site itself can be sort of turned off in this way. So the owner of the eye or the user of the eye actually have the rights to control the terms of this as well. And I think the sort of the example scales from there in a number of different ways. Ryan's work, and I think this question of the drones with the optics and all of the rest of this, also raises, I think, some interesting issues, particularly within the context of arts, of machine vision. And the agency and scale of machine vision. One of the sort of sign of the times is that one of the kind of the interesting styles or curatorial interests of the moment, it actually called New Aesthetic, actually began as a Tumblr blog. And what New Aesthetic was interested in were sort of ways in which machine vision, airport scanners, Google Earth, Google Street View, produces these weird and interesting kinds of distortions and visual effects and structures that were not intended in any kind of way, but nevertheless cohere into a kind of visual profile of this moment. But that they're how machines are seeing the world and how machines are sort of structured and where they go wrong. And to the extent that we might believe that and any new medium really only comes into its own to the extent to which it can produce a new kind of noise, this is the noise that it's produced. But it suggests a world in which machine-based vision, machine-to-machine vision, machines seeing things that other machines saw and interpreting things that other machines saw, and machines interpreting that and interpreting that and interpreting that. Where we're going in Soldier 4, that perhaps in a way all of these NSA tracking devices that we carry around with us with cameras attached to them, proliferating images and all the rest of this. Perhaps the real purpose of this in the long run is to create a visual record for some kind of intelligence in the future to actually be able to interpret what we're about and what the world is and what its sort of terms are, and that this machining vision has a kind of priority. So next, to the question of then to AI and identity. The terms of cybernetics, and of course there's been a lot of interest in cybernetics of lately, but in some very interesting ways, it needs to be understood in terms of sort of its bound history with structuralism, and the ways in which that human culture was understood as a terms of the exchange of signs, and that the terms of human culture as these kinds of binary operations. And historically, especially in France, they're very much bound together. And we see, Beckett and Lacan and the rest were deeply interested in that. And if we think sort of reconstruct this, we have some, very interesting things will come to light. For example, from other things, locating the history of process art, John Cage chance systems and the rest of this, within a kind of history of the algorithm, within an understanding of an algorithmic generative systems, and so forth. And then thinking of them as a kind of precursor to the appearance of those more advanced form of algorithmic intelligence. Or stupidity, or idiocy, and that part. One of the other things I've been interested in this research is this difference between these two terms within AI research of artificial idiocy versus artificial stupidity. Okay. Artificial idiocy, in a way, is what happens when a very simple algorithm is inordinately successful, and the tale gets told in a number of different ways. You've got some kind of intelligence is basically programmed to, turn everything into paper flowers. Right? And all it wants to do is find things and break it down into systems and make something into paper flowers from this as well. And it begins to make more of itself and begins to be more successful and more successful and more successful, to the extent to which the whole, the world and ultimately the universe gets transformed into this. It's kind of the, a version of the gray goo story in this as well. This is when this artificial idiocy is when the machine is so successful that something ultimately idiotic is the outcome, not because it broke down. Artificial stupidity, on the other hand, is when some kind of error is entered into the terms of the reaction. So that if you have an artificial speech system that's going on, unless that speech system actually stutters and pauses and makes little verbal tick mistakes, like I do, then it's not real. You need to introduce error into the system in order for it to perform in a way, right? This is a core idea. Video game programming and other kinds of things, and so forth as well. Okay. Lastly, then, and I'll leave it at that. So perhaps we would have a little bit of time for discussion. The questions of biopolitics, and robotics, which would suggest a lot of different kinds of things. To me, the strangeness of where this would go, and not just in the future, but immediately right now, came when in the same day, I was doing a bit of research on this, but all of these things were posted, articles were posted on this topic in the exact same day. There was a story about a Roomba that had gone a little bit wrong and climbed up the side of a wall and managed to get on top of a stove that was on and couldn't get off. And essentially, this was the first robot suicide. This would have built that it climbed up there and melted down. And the existential angst of the poor Roomba was quite touching. Part of the angst with this as well, which is and maybe some of you may have seen this. There was a story in the Washington Post about these these sort of AI telemarketers call you up. They don't want to give credit cards and the rest of this. Some of them are enormously sophisticated. That can hold ongoing conversations with you, sort of Eliza kind of thing, but much deeper. And this guy's coming up, you don't sound real. You sound like a robot to me. And its replies were, no, I'm real. I'm a real person. Can we talk about the credit card now? And he would keep interrogating it. And it was programmed to have this whole series of evasive replies about its reality, about who it was, and to claim that it was a human. It couldn't disclose itself. It had to pass. It was programmed to pass as a human. And it just, it's touching to hear this. And you wonder, does it know it's lying? Why does it have to, there's something poignant about it. And I think maybe looking back on this, the idea that we would program such a thing to describe itself in these ways may be seen as extraordinarily cruel. Which leads me to the next story, which was this thing about a guy at a university in England, I forget this thing, who was dismissed from the program because he was caught torturing the robots in the lab late at night. He had this whole thing where he set up where he would strap them down, he would do all these menacing, sadistic things to the robots as well. And you think, well, they're machines. It's a bit, I don't know, odd here, but the terms of why this would be exactly illegal, it's sort of, it's apparent, but it's unclear exactly why. The last, probably because he's damaging the property, is more than anything else, but still. And then lastly, which was perhaps in some ways the most interesting on a few different levels, is particularly in Seoul and Japan, there are these, there have been for some time, but there are these very expensive sex dolls. And the most expensive of these sex dolls run about $90,000. Because they have this sort of carbon, their skeletons are made of carbon fiber tubing that goes into racing bikes. And for the most part, the bodies are made out of the same kinds of materials that you would, surgical materials. Like if your skin is burned off, it's replaced with surgical skin, silicone, collagen, all kinds of things. So whatever the state of their medical capacities for replacing human parts are, if you made a person just of that, and then made that into sort of Playboy sort of figure thing, that's a lot what these are. So what enterprising companies have done is to buy whole fleets, if you like, of these robots and rent out hotel rooms, and people go in there and use the robot one way or another and over this kind of period of time. So there's on the flip side then of this, the torture of the robot, and this, well, maybe this space of unexplored intimacy with the robot. Now, on the one hand, it sounds like, well, because it has this simulation to the human that it's sort of working with, but that may not, in fact, be all that's going on there. There may be another logic of care, of connection, a desired intimacy with all kinds of machines, of the material world, of the inorganic, and an empathy with the inorganic, with the object, that may be a much more important and deeper kind of, even a kind of ecological position among this relationship with the material world that may be sort of drawn out of there in one way or another. One might hope. So those are some of the things that are sort of beginning. This sort of the things that are gestating, that are beginning this project. Not at all sure how they will link together one way or another, and what order they want to go in. But as it begins, I wanted to take the opportunity to sort of share the thinking with you and where it was going, and to invite you to invite further conversation about what's at stake here as well. So thank you very much for your time.
I should say a little bit about myself in order to explain why I'm... to explain why I'm going to talk about what I'm talking about. I started out in my career in autonomous feedback control. And I learned very quickly that understanding control theory very well does not position you to design good control systems. Because to design a good control system, you must understand the phenomena very well that you're controlling, and understanding the physics of the phenomena is not enough. You have to understand how you're going to compute the model and what are the errors in the model before you design the control system. So therefore, 90% of my time when I was in industry doing control problems was spent modeling and doing dynamics. So I quit my job at the tender age of 37 or 8, my wife can correct me if I'm wrong, and went back to school to get an education in physics and dynamics, trying to understand how to actually control the systems, model the systems I was pretending to control, only to discover that while in isolation, each of these disciplines are quite sophisticated and mature, but their intersection is still in its infancy. Controls people like to talk about systems theory, and they have books on systems theory, but they don't have a theory of systems theory. They don't have a theory. That is, how to build a system. It was Faraday that said, we should begin with the whole and then design the parts. So what we do in engineering and even at universities is we teach component technology. We say, design this component and this one and this one and this one, and then let the systems engineer put them together and make it do this. Well, obviously, those are not independent endeavors. At the university, we teach the student in dynamics, if that's what you want to model, this is how you model it. And then in the control class, we say, if that's the model of the system, this is what you do with the model, leaving the poor student to believe that these problems are independent. And this is what I learned in industry, and this is why I came to the university 30 years ago, to try to repair that deficiency, that the disciplines of modeling and design of structures and control of structures are not independent. And I have heard so many people say in my lifetime, people in high positions, directors of NASA and so forth, would say, oh yes, we need to get the disciplines to talk to each other. And I would point out that talking is very helpful and to be encouraged, but it's not enough. There is research to be done at the intersection of disciplines that is greater, can be of greater value than another step in each component discipline. It has been said that in the first half of the 20th century, physics drove and enabled new technology. And in the second half, engineering. But engineering has left us with a lot of component technologies without rules how to put components together to make intelligent systems. We make systems and we call them intelligent. That's another thing. But we tend to divide the disciplines. So first we build something, and then we try to model it, and then we put sensors on it and try to sense it, and then we do the autonomous part, design a feedback control system, an algorithm to make it do what you want to do. Well, I spent my life in that business, and there is still no way to do all of that together. So anyway, I want to explain that background before I start my talk, because what I'm trying to do is take a small little baby step in the direction of systems thinking, integrating the disciplines of structure and control design. Now, you could interpret the effort as integrating any two disciplines, fluid and controls, or structures and controls, or acoustics and so forth. But in order to be concrete and specific, I'm going to deal with structures. So if I start with a structure, the first thing I learned in my industrial experience is that if you want to integrate two disciplines, you can't start at the state of the art of either one. You have to go back to fundamental levels and ask how you integrate things at the foundation of the thinking of each of these things. So what could you do with the simplest kind of structural elements you can think of, sticks and strings? You know, there's no bending here, there's just a string, and there's just a stick to take compression. What could you do with fundamental elements like that? Well, the artists do lots of things with them. What could engineers do with them? And why should they worry about such a question? So that's what I want to talk about. So it was Plato, and I'm losing some stuff here. Too much autonomous stuff here. So it was Plato that claimed the straight line is indeed beautiful. Among all the other kinds of beauty and shapes and geometries, he found the simplest. You could think of it as minimalist art. You know, some artists have had wonderful contributions to the world of art by drawing the minimal amount of a line to give the eye and the brain a perception of a three-dimensional object. And but Plato is talking about just the fundamental straight line, and I always like that quote. This is the first structure. I won't call it engineering because it's art. It was created as art. It's 3 sticks and 9 strings. In 1921, this Russian fellow built this structure. And then in 1948, Kenneth Nelson built a structure with sticks and strings. And if you want to use this figure to compare what the Russian Gunnison did and Kenneth Nelson. So if you look at the blue and gray strings, those were the strings that were the components of the 1921 invention of Gunnison. And the red and gray strings were, and no blue strings, just the red and the gray. That was the creation of Kenneth Nelson. And he was a student of Buckminster Fuller, and so this was done as art. It wasn't done for any other purpose. And Buckminster Fuller saw that and thought it was beautiful, and had his picture made with it many times, and didn't say he invented it, but the implication was that he did. And so there was a lot of bitterness between Kenneth Nelson, who was the real inventor, and Buckminster Fuller about this. And so Buckminster Fuller actually gave it a name, a conjunction of 2 words, tension and integrity. So he called it Tensegrity. But as an engineer would say, it's using tension to get stability of the structure. Looks like I'll be playing. So this is a piece of art that changed my engineering approach. I was in the Krullenmühle Museum in the Netherlands in 1992, and I saw this structure, this 80-foot needle tower by Kenneth Nelson. These are stainless steel aluminum bars that do not touch each other. So it rises to this high state and is stiff by just the pre-stressability of the string. So any structure which is pre-stressable and maintains the stability of its shape by the pre-stress is called a tensegrity structure in a loose definition, okay? And so I looked at this and thought, this is a better idea of a structure than any engineer I've ever met, because if you're trying to control, I'm always just trying to control the structure to make it do something. An airplane wing or a telescope or whatever. And so I'm interested in integrating the disciplines of structures and control. And for most of my life, the structures guy would design a shell or a cylinder or some sort of continua and pass it over the wall to the controls guy, and I would put a big heavy actuator on there to torture the structure to do things the structure doesn't naturally want to do, wasting lots of control energy to try to make the structure do that, because the design of the structure and the design of the control system was not coordinated. And here I notice there are no joints. There's no element of the structure that bends, even though the overall structure bends. And very easily controllable by controlling the tension in selected wires or the length. Okay, so the straight line can be beautiful, but what can the engineer do with that, and why should he? So I had a conversation with Kenneth Nelson in his studio in Manhattan in 2001, which went something like this. Artists create inspired structures without doing any math, and engineers often use sophisticated math to design uninspired structures. So why couldn't we get together? So Kenneth Nelson expressed to me his hatred for engineers. He had a commission in Japan once, and he designed this structure which hangs out over a sidewalk, very beautiful. But the engineers in Japan wanted to see the calculations. What are the tensions, to see if it's safe? And he had no calculations, so they made him put a cable from the outer extremity up to the wall, which completely destroyed the artistic appeal of the piece. So I said, I made the offer to Kenneth Nelson, if you, the next time you do a piece, if you just send the geometry of it to me, I'll do the calculations for you for free. He didn't take me up on that offer, but it's still there. Okay, so here's what engineers can do with Tensegrity. So this is 6 sticks and some strings. And there's only 3 parameters required to characterize this structure. Once you decide you're going to use this kind of symmetry, the 2 angles are required to locate the position of that stick, and then you can decide how much overlap between stage 1 and stage 2 you can have. And so you choose that, and you choose these 2. And in the space of those 3 parameters, you can plot this equilibrium surface, which means how can I change these strings without making the structure totally collapse? So getting a rigid structure, you cannot just put sticks and strings together, it usually just fall on the table. So to have a rigid structure, you have to put the sticks and strings together in a special geometry, and you can compute what the set of that possible geometry is. And this is called the equilibrium. And so Tensegrity has some interesting properties. I can change the tension of these strings if I want to change the stiffness from top to bottom. If I want to reject disturbances that are acting on the system, I can, without changing the shape, the distance between top to bottom, I can change the stiffness. So I can change shape without changing stiffness, or I can change stiffness without changing shape. And usually in control theory, you have to have an error before you can correct the system. So you can't just keep the antenna parabolic shape in the presence of some disturbance. You can only do it with high gains in the control. And you can't do it perfectly then, you just have to have an error. But you can actually maintain a shape while making internal modifications of the structure to change its impedance or its stiffness, and in that way reject external disturbances. So this is a good deal for an engineer. And the next question is, if I control this system, I want to move along this equilibrium surface. So if I want to go from here to here, I might move in that path. But I could turn the control system off at any point because I'm moving along an equilibrium surface. I could turn the control system off at any point in time, and the equilibrium will remain stable at that condition. So I'm not torturing the structure to do something it doesn't want to do. I'm simply modifying the equilibrium of the structure to do what I want the control system to do. Okay. So by way of a crude example, aerodynamicists and structural engineers get together and design airfoils for wings. And they've been doing that for 100 years or more. And they know how to get very efficient shapes for the airfoil to minimize drag or get a specific drag to lift ratio and so forth for airplane design. But then the controls people come along and whack off a piece of the wing and put an actuator there and control that flap or that rudder or that aileron to control the airplane, completely destroying all the efficiency that the aerodynamicists had in step one. Now, this is not the way the bird flies, is it? So the bird changes the shape of the wing. You change the velocity or the speed, landing and so forth, you just change the shape. So there is no reason why you couldn't start with this shape and modify to that shape if that's better for the current flight condition. And in the future, this indeed is the way wings will be built. So I can assure you that there won't be any rudders or flaps or elevators in wings of the future. Now, I want to describe the technology and the engineering tools required to do this while designing the structure to have the smallest possible mass that would take the external loads it has to take, and a control system that uses the smallest amount of control energy to make the system do what you want to do. So you can see the cooperation here between modifying the equilibrium of the structure, so I don't need control energy to do that, except there's always a little friction and so forth. So this is easy to see that this is the minimal energy approach to control theory. And if we can not compromise the minimal mass desirability of the structure design, we get both things, and Tensegrity is the only paradigm I know that allows you to do that. Well, I'm not an artist, but I designed a piece that's on campus in the lobby of the engineering building that was inspired by a DARPA contract I had to design a lightweight wing. So DARPA asked, how high can you fly? Can you fly at 100,000 feet or 200,000 feet? How high can we build a plane to fly as the atmosphere gets thinner and thinner and thinner? And the answer to that question, of course, depends on how lightweight you can make the wing. So we made a wing which looks very similar to this. And this was built as a piece of art, but it was motivated by the result of that DARPA search. And our wing was 40% lighter than our closest competitor. So since that time, we've been able to prove mathematically that this is the way to build the lightest weight wing. There's no other lighter method. And that's a pretty strong statement. Whoops. Okay, this is the structure that's actually hanging in the lobby of the engineering building. Well, let's see if we can do this again. origami is a way to build three-dimensional structures. I'm sorry, but I don't know what's going on. So, origami is a way to build three-dimensional objects out of two-dimensional objects, flat pieces of paper. Tensegrity is a way to build three-dimensional objects out of one-dimensional objects, sticks and strings. And every origami can be synthesized as a tensegrity object, but not vice versa. So tensegrity is the mother of origami. So once you do origami things, you can get lots of interesting shape, but you don't have any stiffness. So the advantage of tensegrity is you put that compressive member in there to get stiffness in the right direction. Okay. All right, so this is what engineers can do, but why is that a good way to do structural engineering? So years ago when I was started this work, my friends would say, Bob, I don't know why you're doing this. You know, if you could explain to me what mathematical problem tensegrity solves, I could understand why you're playing with these sticks and strings, but I don't see it. And at that time, I had no answer to their question, but now I do. So if I look at the 5 fundamental problems in structure design, what is the optimal arrangement of material that would take a compressive load with minimal mass? So I have a compressive load here, and I want to know what do I put here that will take that load without failing the structure, but has the smallest possible mass. And I looked in the literature after 200 years of engineering mechanics, and I found no answer to such a question. But so we were able to prove it ourselves, and I'll show you a quick glimpse of that without any the math. I'll just show you what the structure looks like. And then you could ask, well, what is the optimal arrangement of material to have the most efficient tension system that maybe has a constraint for stiffness? So I want a certain stiffness, and so what do I put here to get the best tension member? And the idea for the answer for that problem, that turns out also to be a tensegrity structure. But the answer, the motivation came from study of the spider fiber. The molecular structure of the spider fiber is a tensegrity structure, as it turns out. These beta-pleated sheets in the molecular structure are hard and can take the compression, and these amorphous strands between them take tension, and these compressive members don't touch each other, so it's a tensegrity structure already. And since that's nature's strongest tensile material, that got my attention. And then finally, you could ask about bending. If I have had a cantilever, I have to build something off the wall here to take a load here. So what should I put between here and the wall? What sort of material, architecture, or geometry should I use to minimize the mass to take that load? And the answer is a tensegrity structure. All these tensegrity structures are different, but the answer is a tensegrity structure. So beams and plates and shells do not play any role in any of those 5 questions. So the fundamental start in the education of structure should be sticks and strings. Now, this is the how compressive members go. If I start with this top bar, so this bar, you could put a compressive load here, and then find the diameter of that bar that would take that load before buckling, and then compute its mass. I'll call it M0. Then if I build a structure like this with 4, the blue lines are compressive members, so 4 bars here and 4 strings, then this structure can fail at exactly the same load that one does, so we say it has the same strength. but it has much less mass if alpha is below a certain number. So you compute that. And then if you replace each of these bars by yet another self-similar structure, you can keep doing this until you reach minimal mass. And the minimal mass is at a finite complexity, at a finite number of these self-similar iterations, you reach the minimal mass. And after, in this particular example, after 1, 2, 3 iterations, you're 8% of the mass of the original bar. This example I'm not sure I can get it to work somehow. Anyway, this was another numerical example showing I had a problem where I had to take 44 tons of load, and this was the structure that took the same load as that one, and this one weighed 3% of this one. And another project we do is in acoustic energy. So the speed of sound, if I tap on the bottom of this tensegrity structure, the speed of sound through that material is some number. But then if I pre-stress these strings, I can change the speed of sound through that material, through that system. So by controlling the tension in these members, I can control the speed of sound at multiple points throughout a system, and I can create an acoustic lens that focuses the energy at a specific point, and this can be used in non-invasive surgery. This is how we build the wings, and I've already mentioned this, so I think I'll move on. Antennas, this is the cantilevered, the optimal tensegrity structure for a cantilevered beam, and this is my grandson on his optimal cantilevered beam. This was his bunk bed. He was proud of it because none of his friends had one like that. Now, I'm almost finished. I just want to say something about fractals. So fractals is a nice subject that marries art and engineering, because the people who do fractals in art and math are filling space with self-similar objects, but with no requirement to have any mechanical property. I want to fill space with a guaranteed mechanical property. I want efficiency, and I want to take loads or this way or stiffness that way or whatever. So I want design rules that allow me to take these fractal rules and end up with a structure. The fractals are nice because I can grow the structure in this repetitive way and still have a small mass at the end. Okay, so suppose I just take 4 strings and 1 bar, and I ask, how can I fill up space with that? Well, there's 2 ways, only 2 ways. There's this 3/6 way where if I take this bar and these 4 strings and rotate that by 120 degrees and get another one there and another 120 and get another one here, then I have that triangular hole in the middle, and I fill up the space, and then I'm left over with this hexagonal hole elsewhere. So you specify the radius of this hexagon and the radius of that triangle, and those are the 2 free parameters. You can pick any number and fill space with those numbers, and then you can ask, if I do that, how should I pick those 2 numbers so that this has some nice engineering property? So so for example, this might be 3-dimensional, where this is going from one lower surface to upper surface, and then you get a plate like the one I have over there. So you can have a look at that later if you like. The other way is to have 4-sided objects, and so then if I take this object and rotate it 90 degrees and have it there, and another 90 there, and another 90 there, then I leave a a rectangular square actually here, and another smaller square there. So the radius of those two squares, or the side of those two squares, are the free parameters to fill up the space. Now, if I cut out a piece here and roll it over to form a three-dimensional object. So this is how Smalley got his Nobel Prize in '97, looking at carbon nanotubes in fullerene. So a sheet of fullerene, sheet of carbon fullerene, if you, there's atomic structure in there that gives you these little hexagons in the architecture, similar to the previous slide. But then if you roll that up, that sheet up to make a cylinder, you get properties of I lost the word. The carbon nanotube. You get a carbon nanotube with a certain mechanical property and a certain electrical property. But if you you choose different boundary conditions and roll it about this axis, you get another tube with another mechanical property. And I don't mean a slightly different mechanical electrical property. In the first case, the nanotube could be conducting electricity in both directions. In the second case, it's a diode. It only connects in one direction. It's the same material, but just the rules of closure are different. So I thought, in engineering, why couldn't I do that? Why couldn't I develop some topology and rules of closure to guarantee a certain mechanical property? And so, for example, if I take the 4-4 system and I connect point B to B and C to C and D to D and so forth, I get this structure. And then I can choose the properties in this domain to guarantee that that final structure has a specified set of properties. Okay. I'm probably running out of time here. So we can make a torus. You can make cylinders, you can make lots of things. And I just wanted to show you our latest effort. We're working on a project for NASA to build a habitat in space using these tensegrity ideas. And so this is all a tensegrity structure. This is a torus. If I ignore this white stuff for the moment, just think of this as a torus. And I'll have to ask you not to. I don't have permission yet to distribute that, but
He has to kill you now.
yeah, you can take it. I'll kill you later. Okay, so this is the habitat, and there's ground mass there, and there's water and clouds and vapor, and these water bags on the top protect from radiation. The same level of radiation you get through our atmosphere. Our atmosphere is whatever, 150 miles thick or whatever, but it's equivalent to 1 meter of water. And so the radiation, oxygen, is a good filter for radiation. So those are just water bags. And so the diameter of this thing is 2 miles across. And this is not made from any material from Earth. It's all made from asteroid material. Okay. My computer says I'm finished. So I will stop and ask for questions after showing a couple of pictures. So that's the end of my talk. Thank you.
So I'm taking this back to a much less technologically advanced discussion, but I think a very radical one, and a much more of an art discussion. And this is a picture I like very much of Judd, Donald Judd. I'm speaking about Donald Judd, and because some of you might not know about what his project was, his career and project, I'm going to try to describe that and maybe do a little background on this and how he got to it. But I'm arguing, and I have a new project which I'll try to talk about a little bit if we have time. I'm arguing, one, that Judd is the most radical artist, and that his project, which did not start out immediately, that only developed as he went along, was to undo, I use this slightly arbitrary figure, 264,000 years of image symbolism, and to make an art, a kind of an art that was specific objects. Is this very famous 1964 text he wrote. But when I say specific, I mean non-abstract, non-representational, and abstraction and representational are similar or the same as far as I'm concerned, philosophically, and that they be objects. And what is the object? And I'm talking at a much simpler level than we've just, the kind of robotic object. I'm talking about objects, and including very old-fashioned geometry objects, and what does an object require, and what does an object do at the most basic, but in some ways the most profound level. So before I get into how Judd launched into this project through a series of frustrations with painting originally, and before I forget, I want a couple of comments on the last talk, that, not comments, but stories that come out of that. Before I forget, a Snelson story, for example. I was, as you might have known from the blurb, I was a fabricator for Judd for 25 years and made around 250 pieces for him. And one of the prerequisites, from my point of view, about what a real object is rather than an imitation object, or a kind of, we'll call this an object, but it's actually a sculpture, is delegation, and a kind of a relationship in a kind of composer, musician, architect, builder relationship. And I'm going to try to talk about it, or in the questions afterwards, how extreme that delegation was, really extreme. And I'm trying to get that information out into the scholarship about Judd, because I feel quite strongly that if there's a pie chart on Judd scholarship now, there's about 1/3 of the information missing, because people don't understand how the objects got built, what the relationship is to what the objects mean. And but before I lose the Snelson story, which delighted me, and Judd, I'm not going to say that Judd was hostile to engineering, but there was a very large plywood piece. I made pieces out of some other materials, but mostly plywood, including some very difficult ones that took a lot of seat of the pants reckoning, non-mathematical, semi-mathematical kind of figuring out. But there was a very large piece that was 80 feet long, 12 feet high, and 4 feet deep, and the material was 1 3/8 plywood, with a lot of angles, such as with interior pieces set at angles, some of which were so steep that a bevel on a piece of 1 3/8 ended up with a 7-inch bevel face, with a paper thin kind of point to it. Anyway, it was a very difficult piece. It could easily have been a failure. I worked on this piece for 9 months. Took 2 months to install it in the at Castelli Gallery on Green Street. And it had to be, it was against a wall, and on the floor it had to be, it was so heavy and so big that you couldn't build it and then push it back to the wall. There had to be a wall built with an opening in it within a couple of inches of the size of the piece, and you had to work from the back. And so there had to be this 3-foot passageway behind it where you could, I mean, I think you would have loved this piece. There are all kinds of wires. It looked like, it was invented by me, but it looked like a 19th century bridge with trusses, kind of homemade trusses and things. And all this stuff was from the back. There was a door in the sheetrock over here that at the very end of the installation was going to be closed up. And I was in this gallery for 2 months, and it was 2 days before the opening. Judd had not seen the piece, finally couldn't stand it anymore, came over to see whether it was going to happen or whether it had fallen over or whether it was going to be done on time. And we were just about to close up this door, which would have given you the effect of the piece being completely flat against the wall, and the only way of working on this was from the back. And I said, Don, we're about to close this. Do you want to see the piece from the back? It looked like, it was wonderful if you like structures or extremely low-grade engineering. It's not engineering at all, but it was like, how did you make this piece stand and not these long spans, not warp? Light bulbs on strings. It looked like a part of the coal mine in Chicago at the Museum of Science and Industry. It was really interesting. And I said, Don, do you want to see this? We're about to close this. And he said, no. And I was surprised a little bit, but I had already been working for him for 10 or 15 years. And I sort of realized what he was doing with that. He doesn't want to see that and how it's made. He doesn't want to talk to engineers or engineering concerns from the fabricators like me or Bernstein Brothers or some of the other fabricators who are always going to be talking about making half-inch plywood into 5/8 or 5/8 into 3/4 because it's a little less likely to warp. He wants the piece, he does a drawing or does a description of the piece, and he wants the fabricator to figure it out. He doesn't want to start thinking like an engineer because that changes what he wants to do. He poses a problem. Can you do it? And largely that worked. I could give you some examples, a few isolated examples where it didn't work, where there were tears in that process. But this delegation worked for him from his point of view. This is a anti-engineer story, a little bit. The other thing I want to explain early on is about space. Judd has a very geometric or 2,000-year-old view of space that claimed and wrote and said and lectured that there is no such thing as space, artistic space. It's only made by the artist by locating a point or a plane in that space, and before that there is not some kind of space as in ether or oxygen or something, and the artist makes the space with an object, and the object can only exist in space, and that there's this very fragile and hard to achieve relationship between an object and space. And near the end of his life, he wrote about space more and more, that this was what he thought was his major contribution to art, a kind of an interest in space. And how do you do that, and what are the qualities of an object that you need to do that? Because an object that gets too complicated or too too much of an image, weighs the balance toward the object and away from the space. Or an object that becomes damaged or fenced off or sits on a pedestal. We just had this discussion earlier. or is badly overlit, or overly dramatic lit, or any of these. There's a lot of things that vote against the success of this space object relationship. And I wanted to just come back to space because you had mentioned space, and I wanted to mention in a different sense. And Judd's kind of space, what he's talking about space is an artistic or architectural space. He thinks the very best architecture actually creates space. Most architecture doesn't, or it creates poor space or non-existent space. And the very best art also does it. And that's what he's trying to do. So, because I didn't want to forget this, because it was related to your talk, but Judd started a little bit of background on Judd. If you don't know him already, he's born in 1928. He's a painter in the 50s. He's taken some philosophy courses at Columbia. The philosophy that he's interested in is 18th century empirical philosophy about the observer and about how you understand the information. It's not advanced 1950s philosophy. It's not Noam Chomsky or other latest philosophy. It's quite an old-fashioned kind of philosophy about experience. And we could discuss this later in questions, but against abstraction, I would say. And his problem, this philosophy, this kind of being imbued with this kind of heavy dose of philosophy, not heavy philosophy, and this is a couple of college courses in philosophy. He's not a philosopher. It's a mistake to paint him as that, but it was a kind of a simple story, very deeply taken to heart, and this basically eventually destroys painting for him. He wanted to be a painter. He tried very hard to stay a painter. In the 50s, in New York, all the really serious stuff, as far as he's concerned, was painting. It's Barnett Newman and Rothko and Reinhardt, and Judd was always very ambitious, not in a monetary sense, but in a make a difference, start history kind of sense. And he tried hard to play in that league with those at that level. And his philosophy was ruining it for him because illusionism, the two major shoals that painting crashed onto, as far as he was concerned, were illusionism, the claim that this is that, or this is not that, or and composition, the kind of willful, expression-based arrangement of things by the artist. There's a lot of reasons why this was so annoying to him in the 50s, but one of them is that abstract expressionism had run these into the ground as far as his generation was concerned, and his attempt to make a philosophically tenable painting led him eventually to making found object paintings, of which there are only so many you can make, and those kind of migrated eventually into found objects, floor pieces and wall pieces. And for a couple of years, Judd always claimed he didn't make sculpture, but I think for a couple of years, 62, 63, when he was making the pieces himself, I think it's fair to say that he was a sculptor. He ran in the early 1964. Somebody mentioned, you mentioned 1963 is this really important year. For Judd, 1964 is this very important year. 1963, he has this very important, well-regarded show at Green Gallery in New York. And you have to know, as a background, that Judd was a critic, as well as an artist, and which is he was very well suited to getting his message out, because he could write every review he wrote about somebody else was kind of about himself. And I don't want to take anything away from this Green Gallery show, but this show is very successful, and These were objects, plywood pieces he had made himself, and he was running up to the limit of what he could do with his hand skills. And exactly 50 years ago now, in January 1964, he took a drawing to a sheet metal shop on 3rd Avenue and said, "Can you make this?" And originally this was to take care of a problem that he didn't know, he couldn't work at an anonymous or at a professional enough level galvanized iron. But by the end of his life in 20 years, almost 20 years ago now, this getting your pieces fabricated had become an essential situation for the piece to be considered really an object. And I think Judd was right that after 1964, when the pieces are being made by other people, not by him, and at great delegation, that it's fair to call them objects. And there's an interesting discussion about what objects mean. Objects have been running through all these talks. What are its qualities? One of them might be, in an old-fashioned sense, that somebody else made them, not the artist didn't make it, because there's always going to be expression either in the object or attributed to the object if the artist makes it. But I started making pieces for Judd in 1971. I started working for him in 61. And this didn't all become apparent to me right away, but only over time. But I also think the possibilities of delegated fabrication became more apparent to Judd over time as well. And there's a wonderful essay, his last essay, about the one that's so much about space. And it's also, speaking of sticks and stones, I think you would like this article also. He uses the example of arrangement of sticks and stones to discuss objects and composition and how can you avoid composition. And there's a number of ways of trying to avoid composition. I don't know whether we have time to get into all of them, but foundness is one of them. Found colors, found number systems. Fibonacci series, for example, is not advanced mathematics at all, but it's something several hundred years older than he is. Found materials, galvanized iron, Douglas fir plywood. Fabricators, the use of fabricators is a kind of found material. If you can take an idea and transfer it to into the rules of sheet metal work, or into the old-fashioned, quite the 19th century, 18th century rules of carpentry, it's another kind of delegation, it's another kind of foundness. You're delegating into these found systems. You're not reinventing them. So I have another small story about delegation. I live on Green Street in New York, and Judd lived on, Judd's place is on Mercer Street, the next street over. And I was I'm not saying this for the wrong reasons, but I remained friendly and close to him his whole life after I met him, and which isn't true of everybody who worked for me, because he was ferocious about what he believed. We talked about the Ponza thing a little bit earlier today. But I bought, my house is on Green Street, and I bought it in 1973, partially because I needed a shop to make these things, and I needed a better shop. And there was a standing invitation for him to come over and look at pieces. That's where he made more than 200 pieces. Or he'd have coffee or have dinner or something, but he only came to that house once, right after we bought it, because he liked old houses. And so the opportunity to look at pieces and we should use the plywood the other direction, or we should use, it was there. He could have come over if in a moderately strong rain without an umbrella and looked at these things, and he didn't do it. And it's related to this other story of the so-called Saatchi piece on Green Street. He doesn't want to know that stuff. He doesn't want to be polluted by it. Is too strong, but he doesn't want to be influenced by it. That's up to these other disciplines or these other kind of. There's an expression that I like quite a bit, a very old expression that maybe not everybody here knows, but there used to be a kind of a compliment for, say, that somebody's a good mechanic. That didn't mean a car mechanic. It meant a good mill operator or a good, what else, a machinist or something like that. It was a very high compliment in those kind of fields, in the, like Czechoslovakian, machinist with rimless glasses, he's a good mechanic. Oh, he's a good mechanic. But I think that Judd's transferring these into people who are good mechanics, not, I'm throwing a lot of stuff at you at once, but not Rolex watch perfectionist mechanics, and for a reason I'll talk about in a second, and not kind of neighborhood mechanics, neighborhood practitioners who just happen to be conveniently nearby. If you were going to be, if you're properly, from my point of view, properly a Judd fabricator, you have to hit a middle spot where the piece looks exactly right, but it's not poorly constructed and it's not overly polished, because it's always possible, if you're good at what you do, to take it a little bit farther. And either of those things is a distraction that puts too much spotlight on the object. And when the object becomes highlighted in one of many ways, damage is another obvious way it can be highlighted, or being on a pedestal, or there's lots of ways an object can be damaged. When the object starts to take precedence over the space that it hopefully creates, you've lost your project. You've lost part of your project, and it just becomes an object, and it becomes. So it's installation is pretty important with Judd also, but the delegation was not just delegation per se. It had to be delegated in a way where the pieces got made in a business-like, good mechanic kind of way, but not overly or under. And the point you're trying to hit when you're making these is like right down the middle. The way it should look the way it's supposed to look, and it shouldn't be more or less than that. One of the things I'm working on right now is I think I mentioned this, but I think that I think there's a good third of Judd writing scholarship that is missing, and one of the, so that if you are really interested in Judd and you get everything you can find on him and put it on a very long table and read all of it, you're going to feel like you've read the same thing several times by the time you're done, because I think that the scholarship on Judd has become kind of stalled because the object has been sort of left behind, or people don't quite know what to do about the object and how it got made. There's usually a short or very short paragraph about factory fabrication in a book about Judd, but it's not known, or it's suspected and feared how much this people are afraid that this delegation somehow weakens the objects or weakens the art. In fact, I think it strengthens the art. I want to see some new work done on the issues that come out of Judd. Virtually all of his work has been fabricated. All of his work since 1964 was fabricated. So this means that of the pieces that weren't fabricated that are three-dimensional, there's about 18. And of the pieces that were fabricated, there's 3,000, something like that. And I want, since I was close to this, I want to see this a kind of a realistic place, a realistic kind of understanding of how pieces were made and why they were made that way, and what the implications of why they were made that way. Implications into the future, like what can you do about damage? Can you risk the pieces the way Judd insisted that you risk them? No lacquer on the copper and brass, no pedestals under floor pieces. Can you risk them that way, or was he uninformed? And the grounds. A story. There was a Judd retrospective at the Tate in 2004 that created a little bit of a crisis. I was still working for the Judd Foundation at the time, and I tried mightily to get all I arrived to work on our pieces, and the gallery and the Tate had already put several of the really old pieces on pedestals. Absolutely T-shirt motto worthy, wrong thing to do with Judd. And I was able to get all but one of those off the pedestals. And the one that didn't get off was a complicated, slightly suspicious story behind it. But the danger of pieces starting to go on pedestals for their own protection, and what's wrong with that, and what happens if you do what Judd said, which is put them right on the floor, kind of inspired me to try to come up with a better theory of Judd, based on what I already know and what I've spent 45 years thinking about. You have a situation where you have an art that's has become very expensive, often is made out of materials that are, it'd be better if we didn't have to use the word fugitive, but that are not forever materials. Galvanized iron is a sacrificial material, in the same way that white house paint is on clapboard houses. Copper tarnishes. So you have a very expensive kind of art made out of materials that are not marble and bronze. Judd, in an engineering-like way, Judd is not interested in mass, not for engineering reasons, but he's interested in space, and he's even thinking about points and lines. And so many Judd pieces are made as thin as possible because he's not interested in mass, right on the edge of too thin. Some occasionally on the other side of too thin. So you have these. Often they're very heavy because they're big. So you have heavy, thin, expensive, fragile materials that have a rule that they should not be protected by a pedestal or lacquer. Judd's, if you've read anything about Judd, you come across the idea of permanent installation in Marfa, or permanent existing. Judd was very conscious of his place in art history, and these pieces, though they're made out of so-called fugitive materials, were not intended to disappear in some kind of Smithson-esque way. They were designed to be there, and we talked earlier about the Issei model, right? So if you try to put all these things together, it either looks like Judd didn't quite have it figured out, or did he? And the place that you always have to come back to that makes a difference between other artists. I mean, there are many artists who use fabricators, especially now. But in 1964, there weren't very many when he started doing it. There's a handful, and it was hot stuff. It was a hot topic. And Marc de Souvero, who's a kind of, I think you would like Marc de Souvero if you don't know him. He's not unrelated to Snelson in the way he did the pieces. Who was a friend of Judd's, in 1964 told said to Judd, Don, you're not an artist anymore. You didn't make the work. Which the Suvro later apologizes for and says, I don't know why did I say that? But there were a lot of people who tried to stamp out the fabrication part of things early on, the critics, the abstract expressionist critics who understood immediately what, if this were allowed to stand, what that would mean about painting, for example, conservative or not even hugely conservative voices everywhere. And like if the artist can make the piece but doesn't have to make the piece, other artists had to grapple with that subject also. But what it means is if the artist doesn't make the piece, certain things, certain implications are possible about what happens if damage occurs. And we already talked a little bit about what damage means to an object. It's suddenly a piece that has no artist's handwriting on it, no marks, detail, marks, whatever we're going to call that. It starts to pick up marks and detail. A really simple box on the wall with only maybe a smattering of makers' bending marks from the early to mid 19th century kind of bending techniques that it takes to bend sheet metal is different from damages and scratches. And if you, I know this from, even though I've worked for Judd for such a long time, if you have a very simple piece and you suddenly have a scratch in the lower right-hand corner or 3 scratches or something, or a bend or something, the eye immediately goes to it because we've all been trained at one point or another to look for detail. A Titian, for example, what should we say, has 300,000 details arranged in a certain way. And if you start to pick up details, the eye goes immediately to that detail and sabotages the rest of the piece. And I use a quite old-fashioned example, like a LP example on that, but let's say your favorite LP that you, it's either yours or your parents or something, your favorite 10-inch record is a Beethoven record, and you know that there's a scratch at minute 11 and a half. The first 11 and a half minutes, you know it's coming, and after it's happened, you know it happened, and depending on how much you care about that kind of stuff, there's a serious sabotage of that piece of music when that happens. And Judd pieces are subject to this as well because of the no detail, suddenly detail kind of thing. So what do you do about that? Do Judd pieces, are they fated to become more and more kind of sad? There's one school or one opinion on that. There's an art piece should show the signs of its own age and its own history, which you hear more than you might think. But and patina, subjects, the topic of patina and aura and all these kinds of things that were pretty foreign to Judd. Not just pretty, they were absolutely foreign to Judd. And what are those things anyway? Those topics are, we had this discussion about art and history, and the fact that art history can be, there's a certain point where art history separates into art interests and history interests, slightly separates. And when people are talking about pieces showing the history of their history, they're kind of more interested in the history and kind of less interested in the art, especially when you have a rigorous kind of program like Judd does about objects that should be clean and why they should be clean. So the big elephant in the room that nobody really wants to talk about, and that seems to threaten a lot of people, is what do you do if you risk pieces right on the floor or right on the wall, unprotected, like he wants, and damage occurs? What can you do, and how far can you go into, say, replacing parts? And how inauthentic could it be in certain situations, specific situations, if you don't do those things, if you try to do a patch job on a piece of broken plexiglass. And I mean, we could use plexiglass as an example, but plexiglass is a flat glass-like material. It's poured on glass to make it glass-like in terms of flatness, and it's clear. It's a certain thickness. Clear. It's usually it's often transparent. It's a certain thickness throughout, within a little bit of a tolerance. And if you, I've done. I love things like this, but my actual income comes from restoring Judd pieces, and I've spent days and days trying to make a piece of broken plexiglass look like it's not broken. And philosophically, you could say this is a kind of illusionism, and to make something look like it isn't. And you also will understand immediately that it's not like wood where you could possibly steam out a scratch. The only way you're going to get that visual scratch out there is by removing material, and which gives you a kind of a cupped shape, which no longer reflects the way it did when it was flat. And depending on how much you've taken away, it might have a different transparency. So, and Judd never selected that piece of plexiglass in the first place. And a lot of the pieces I made that involved plexiglass, and I know the oldest of the fabricators, I knew them really well, Bernstein Brothers, and I know they did the same thing I did. When you have a piece that involved plexiglass, you bought extra plexiglass, because if any of you have ever used it, you cut it, you make sure the masking is intact before you cut it to shape, you get it ready to put it into the piece, you peel back the masking, and though there was no break in the masking, there's a damn scratch there. So are you going to spend 2 days trying to get that scratch out in the way we talked about, or are you going to get another piece of plexiglass that you bought extra because you know this can happen? And so in some ways, I'm throwing some topics out here, but in some ways that replacement of the piece of plexi, 40 by 40 by 1/8 thick plexi, when it's being fabricated, or at the time it's being fabricated, is already a kind of restoration by replacement. And you have to ask the question of like, okay, so is that different than doing it later, and why? And is it seriously different than later, or is it not? But it raises the question, and the ultimate question, the one that gets people that's quite a heavy topic, is how much can you replace? Can you restore by replacement? Given the fact that the artist didn't make it, and possibly in some cases the artist didn't see it, does it give you? Do Judd pieces have a somewhat unique chance to remain on the road, to use a car? We talked about Bugattis earlier on, and I think there are many clues to this discussion to be had from outside. Now, who was it who talked about outside sources? One of us talked about getting people from other disciplines. I think you did, right? Like, you're better off with some to going outside the field sometimes than to stick within the field. And I think that there are clues to be had on this from other fields where the object has to be functional. And we don't have enough time to talk about functional in this case, but Judd pieces have a certain function, and they fall out of functionality at quite a low level. You could have I don't want to. The cheap examples would be, a Roman marble copied from a Greek original with no head, 2 legs missing and 1 arm missing. You could say 55% damaged, considered show-worthy at the Met, for example. And a Judd piece with, say, 1%, 0.5% damage or 1% damage is often unshowable and unsellable at this very low level because of what I talked about. the accumulation of detail and damage is, we talked about this earlier, damage is often not meaningful damage, it's often stupid damage from poor handling, and it's almost never bullet holes from the Revolution of 1848, the kind of damage that you might be tempted to keep for symbolic reasons. So the final thing is what I'm trying to do, this project I'm trying to do, which is I'm trying to set up an advanced Judd issues, Judd in parentheses, because I want it to be wider than just Judd, but issues that Judd embodies really well, I think. Judd issues program in Scotland, in Orkney, in the Orkney Islands, which is as remote as Marfa is, except it's not Marfa. And I want to have people write new takes, not necessarily the same cast of characters, and I don't even think, I'm not even sure whether being an expert in Judd is a plus or a minus, but philosophers and architects and critical theorists and art historians, and to go to Orkney for 2 months and write on subjects such as abstraction, function, objectness, performance, originals and copies. We talked about the Issei model of originals and copies, like questioning this kind of question of questioning the subject of original and copy, and how it's always been considered to be very important, but how important really is that? And are any Judd pieces really original in the way that that's usually used, which usually means the artist made it? Final example on that original and copy subject, and then I'll stop, but his famous type of piece, the so-called stack, which you might know. It's a series of usually 10 boxes arranged vertically on a wall with the space between, let's say a stack is 9 inches in a vertical dimension, cantilevered speaking of cantilevering, it cantilevered quite far out, 30 inches sometimes. And there's 10, and if they're 9 inches, the bottom of the first one's 9 inches off the floor, and the spaces between are 9 inches. The spaces are equivalent to, except for the thickness of the material that makes the box, are the free space between is the equivalent to the captured space inside the box, and they ideally are exactly the same, or as close as a sheet metal shop can make them. And I've installed 1 million of these things, and when you're installing them, technically any one could be the top unit. Mostly they don't differ. So is the first one, let's say the top one, the original? Are the other 9 copies of that? Are they all originals, multiple originals, or are they all copies of what, like the drawing, the purchase order from to the fabricator? And you see out in the show, the show outside, you see some purchase order documents. And I have some, afterwards, if people want to look at the other side, which is pretty interesting, because we could only do one side, but I've got a few loose ones, and the other sides have timesheets on them. JO, 1 3/4 hours, on Tuesday, and it brings that kind of fabrication birth of these pieces back fast, I think. And so I want to see this stuff. I'm thinking of this program as being a 5-year program with writers, 1 or 2 a year, going to faraway Orkney and writing on these subjects, and then seeing them discussed in a program like this at the University of Edinburgh, and get published and disseminated. And maybe we get some new stuff. It's meant to produce new ideas on Judd, and I've been asked, why don't you just sit down for 2 years and write the book? Which I might be doing at the same time anyway. But I'm interested in many voices on these subjects, not just my own. Even to the extent of if somebody just really disagrees with me on these things I've been saying. So I like to just see it become a good discussion again. So that's me, and so I think you're going to go into a question period now, right?
We could have a short discussion now. We could move on to reception since we are somewhat over conversation there.
Yeah.
What would you prefer?
Let's go out.
Shall we have the conversation outside?
Yeah.
All right. Thank you.
Thank you, Jude.